Welcome to my channel. In this video, we'll discuss five problems on Laplace transforms from GATE papers. Now, before discussing those problems, I want to highlight the special features of Laplace transforms. Those will be used to solve those problems. So briefly, we can say that if we have a signal, continuous signal x of t, its Laplace transform is capital X of s, where the relation is capital X of s we can get from x of t taking integration x of t e to the power minus st and dt. We will consider one-sided Laplace transform 0 minus to infinity. And inverse Laplace transform xt we can get, okay, we will not consider inverse Laplace transform. So if this is known, we can find out its inverse. Right. Now, for few important signals, first of all, for unit step signal, ut is Laplace transform is well known. This is 1 upon s, and that is very easy to prove. Okay, you can find this one. So Laplace transform of ut. So if this is ut and e to the power minus st dt, you see 0 minus to infinity, and ut is defined this way from 0 to infinity. It is 1 and left side is 0. That is your unit step input. So this is 1 and time will be from 0 to infinity again. Okay, e to the power minus st dt, and integration of this one is e to the power minus st, and you are integrating with respect to t, so it is minus s, and if you put 0 to infinity, then you see at infinity it is 0, at 0 it is 1, e to the power 0 is 1, so that is minus minus plus, thus you will get 1 upon s. So this is well known. Okay, and second one is e to the power minus at ut, its Laplace transform is 1 upon s plus a. That also you can find out. So you see this one, so e to the power minus at ut, so at, so if you multiply e to the power minus st dt 0 to infinity, and you will see this we can combine e to the power minus a plus s time t dt, and you see this expression and this expression is exactly same except s is replaced by s plus a. So this 1 upon s, here we can replace this value by simply 1 upon s plus a. So these two are important signals. Second one is exponential signals. First one is unit step signal. Okay, right. And you know that Laplace transforms is primarily used to solve differential equation. Okay, so that property we should understand. So first property is that if xt is a signal, its Laplace transform is capital X of s, then if you take derivative ds dt, then its Laplace transform will be s times capital Xs minus small x of 0, right? So that proof is also very simple. So you can skip these proofs if you know this one, then you can go directly to the problem session. But for all of you, I want to repeat it. Okay, so we want to get this one of Laplace transform of this one. So Laplace transform means signal is dx dt. So with this we will multiply t power minus st, then integrate it from 0 minus to infinity. Right? Now we can take partial fraction, partial this one by parts. So integration by parts we can go for. So e to the power minus st we can take this one outside, and integration of ds dt time dt. So this is actually this one, and its limit is we can consider 0 minus to infinity minus derivative of this one. And you see this integration, so this will cancel out. This integration is simply x of t, right? So that I can replace here. So derivative of this one is how much? So it is minus s e to the power minus st. First derivative of e to the power minus st, then integration, that you can replace only xt, and then e to the power minus st. This part is there, the dt only. Okay, then dt, and limit is 0 minus to infinity. Now if you see here, it is xt e to the power minus st. It is 0 minus to infinity minus minus plus s times s is outside. This is the integration only 0 minus to infinity e to the power minus st x of t dt. And now we can notice that, so the e to the power minus infinity is becoming 0. So first one is 0 minus, second one is 0. So if you put x of 0 minus, and e to the power 0 is 1, so it is x of 0 or 0 minus, you can say, right? And plus, now this is simply capital X of s, right? So it is s times capital X of s. So thus we have got this one. Okay, s times capital X of s minus x of 0. That's all. Now if you have higher derivatives, right? Now if I have second order derivative, d square x dt square. Okay, so what is the Laplace transform? Okay, now you see this one we can rewrite that d dt of Laplace transform of dx dt, right? That we can consider. So already we have considered this one dx dt. Its Laplace is s times xs minus x of 0. Okay, now this is my signal, its derivative. So what I write? I can write that it is a s times of Laplace transform of dx dt, because this is x of s, this is my right now signal is derivative, so it's s into that Laplace transform minus this signal at 0, means ds dt at 0, means I can write x prime 0, right? Now we can simplify it further. This one is s, and Laplace transform this one again, it is s xs minus x of 0, it's minus x prime of 0, right? So this will give you s square x of s minus s x of 0 minus x prime 0. Be careful here, okay? So if you extend in that way, suppose if I want to compute the third order dtq, so I think it will be sq xs, then minus s square x of 0, you start from x of 0, then minus s x dash x prime 0, first order derivative, okay, at 0, minus x double prime 0, like that. Okay, so we'll be using these relations to solve those problems. Now quickly we'll move to that one. So first problem, you see this inverse Laplace transform of this one. It is a gate 2019 EE paper, and answer is given as C. Now let us find out. So this is h of s is s plus 3 upon s square plus 2s plus 1. Okay, so these we can write as s plus 1 that square, and we will go for partial fraction. Okay, so can I write it this way, that this is 2 plus s plus 1, because s plus 3 is numerator. We can write in this form 2 into s plus, because s plus 1 will should be one term that should cancel out. Okay, so now we'll take partial fraction. So very simple division, only 2 upon s plus 1 that square. Okay, and plus s plus 1, and this is s plus 1 square. Okay, so this one will be 2 upon s plus 1 that square plus 1 upon s plus 1. Okay, now here we'll be using one more property. Okay, so if xt is Laplace is capital X of s, then txt its Laplace is simply minus dxs ds. Okay, that he can easily prove it. So you can start from x of s, then take derivative. You will see that dx of ds equals to minus, and that will be derivative Laplace of minus t times x of t. Okay, t times xt only. Okay, be careful. So now using this relation, we know that ut is Laplace. We have got 1 upon s. So tut, the ramp signal, it will be derivative of 1 upon s minus sign. So you will get 1 upon s square. So ramp signal is 1 upon s square, right? So if it is 1, it will put t into, you multiply it by minus t ut. So I have said that whenever it by minus t is multiplied, so s is replaced by s plus a. Okay, so here it is 1 upon s plus 1 that square. That means 1 upon s square, its inverse is t times e to the power minus t ut. Okay, that we are going to use it. So now from here we will get the inverse h of t would be, so inverse of this one is 2 is multiplied here, then 1 upon s plus 1 the square is t times e to the power minus t ut, and this one is simply e to the power minus t ut. So if you combine, you will get 2t e to the power minus t plus e to the power minus t, and that one you can write ut as well. So this is the answer. So answer C is the correct one. Right? Now next. So already, so you see initial conditions are given 0, and the YS is the output of the system. So if this is my system, h of s given, and impulse response is h of t, input is x of t, and output is y of t, and we know that it is in convolution between xt and ht. But if you take Laplace domain, then it is capital X of s, and this is your y of s, and it will be capital H of s multiplied with x of s, right? So in this case, h of s, so here h of s is given as 1 upon s, right? And ut, input is ut, so xt is ut, thus capital Xs equals to 1 upon s again, because that we have seen. So what is your y of s? Capital Y of s is h of s times x of s. H of s is 1 upon s. This is also 1 upon s. So this is 1 upon s square. So now we'll need to take inverse. So y of t, that we have seen, that ramp signal is having Laplace transform of 1 upon s squared. So it is t ut. Okay, so answer is B. Correct? Next. Now for this one, you see there is one differential equation given and input is specified here and initial conditions are also given. Y of 0 is 0 and dy dt as 0 is also 0. We need to find out Laplace transform of yt, means y of s. Okay, so first we'll consider this xt. Okay, so what is xt given? Xt is given as this is 1 for this one and 0 otherwise. So what is the safe? So you see this one I can consider 0 to 2, it is 1, it is 0, it is suppose 2, 0 to 2 it is 1, and beyond that it is 0. Everywhere it is 0. This is 0, this is 0. So this is your xt and that time in magnitude is 1. So this one equivalently you can write we can consider one ut signal 1 and we can subtract an ut signal starting from here. This is 0, this is 0 and this is 2. This height is 1. So this is your ut and this is your u of t minus 2. So if you see 0 to 1, this 1 minus 0 is 1 and beyond that 1 minus 1 is 0 and left side is also 0. So this gate window we can consider as, so this xt we can write as ut minus u of t minus 2. So here there is one more property. Okay, so if t minus capital T, so there is one more property is there. If xt is Laplace transform is capital X of s, then x of t minus capital T, its Laplace transform will be e to the power minus st times capital X of s. That proof is also simple. It's not very difficult. Okay, so that okay, let us prove that one. I'll prove that one. So before that, using that this one, can we find x of s? What is x of s? So this is 1 upon s. It is minus. So as it is delayed, so it is e to the power minus 2s multiplied by Laplace transform of ut, that is 1 upon s. That means 1 minus e to the power minus 2s by s. Right. Now let us prove this one first and then we'll use next part. So can I consider this one, that x of t minus capital T, its Laplace transform I want to consider. That is your x of t minus capital T e to the power minus st dt, 0 minus to infinity. Okay. Now if I consider this one, that t minus capital T equal to tau, if I replace, then dt equals to simply d tau, right? So can I write that this one as, it's x of tau and this is e to the power minus s what we can write is there, and t I can replace, it is t plus tau, and it is your d tau, and the limit, okay, we can change it to remain infinity, and this one, okay, whenever it is 0, tau could be from minus tau minus t, whatever it is. Okay, so now this one, what you can do, so this is e to the power minus st, it's outside, and this is your x of tau, e to the power minus s tau d tau, it's infinity, so we don't put our limit. So this will again, so if I go for double sided, then it's entire integral minus infinity plus infinity. So in that case, it will be e to the power minus st, and this is your capital X of s. Okay, so if we go for the double sided, then there will be no confusion. So it will remain minus infinity. Okay, for double sided. Right. So this is the result. So x of t minus t, e to the power minus st capital T. Okay, that delay. So now you consider this derivative. So differential equation given d square y dt square plus 5 dy dt plus 6yt equals to xt. Now you take Laplace transform on both sides. So what you will get? If you take Laplace transform, so what you will get? So first one is a square capital Y of s minus s times y of 0 minus y prime 0 derivative that we have seen, plus 5, Laplace transform of this one is s times y of s minus y of 0, small y of 0. Okay, this is small, and this is 6 ys, this is your capital X of s. Now you have seen that both this is 0, this is also 0. So this is 0, this will become 0. Okay, this will become 0, this will become 0. Okay, so just we can collect this one, that this is y of s, here it is a square, here it is 5 into s, and here it is 6, and xs is given as, so already we have computed, 1 minus e to the power minus 2s by s. So therefore, what is the ys? Ys will be 1 upon 1 minus e to the power minus 2s upon s, and this one, this s square, this one, we can have factors s plus 2 and s plus 3. So this is s plus 2 and s plus 3. Okay, so this is the answer, y of s, and this is the correct answer, it's matching, right? Okay, next question number 9. Now again, one differential equation given, and initial condition is given as 1, and unit step function, and ut is unit step function, signal ut, this is ut. Now we need to find out yt. So what we will do, we will go for first Laplace transform, then again we will take inverse Laplace. So we'll start with this one, y dot t plus 5 yt equals to ut. Take Laplace transform, it will be x s times capital S of s minus y of 0 plus 5 into capital Y of s equals to, this one is 1 upon s, right? Now this is given So this 2 I can collect first. So this is s plus 5 times capital Y of s, and this is minus, and this is given as 1 equal to 1 upon s. So capital Y of s would be 1 upon s plus 1 upon s plus 5. Okay, so if you simplify this one, we'll get 1 plus s upon s into s plus 5. So now we can have a partial fraction. So this y of s, we can have two parts, s, and this is s plus 5. Now to get this coefficient, I'll put s equal to 0 everywhere except here. So if I put s equal to 0, this is 0, this is 0, this is 1 by 5. 1 by 5 is 0.2. Okay, so this is your 0.2. And now s equal to, for this part, here this coefficient s equal to minus 5. So I'll put s equal to minus 5 everywhere except this one. So s equal to minus 5. So 1 minus 5 is minus 4. This is minus 5. So minus 4 by minus 5. Minus minus cancel out. 4 by 5 is 0.8. Okay. So this is 0.8. So now easily you can take inverse. So y of t is 0.2, and this is your simply ut. This is 0.8, and this is e to the power minus 5t ut. Okay, so 0.2 plus 0.8 e to the power minus 5t, right? 0.8 e to the power minus 5t, that times ut. So answer is A. A is correct answer, right? So I hope you understood this thing. Next one. Again, one differential equation we will need to solve with these initial conditions. Y of 0, y prime 0, that is both are 1. Okay, and the differential equation is this one. So d square y dt square plus 2 dy dt plus y of t, and this time it is given 0. So just take Laplace transform on both sides. What you will get? First one is s square capital Y of s minus s times y of 0. Be careful. Minus y prime 0. This one plus 2 times. It is s times y of s minus y of 0. And this is your capital Y of s, and that is the right side is 0. Okay. Now this is given as 1. This is also given as 1. And this is also given as 1. So just we replace all those things. So first we can collect this and this and this, these three. Okay. So what we will get? This is your s square. This one is plus 2s. And here it is 1 times y of s. Then this is minus s. This is minus 1. So this is your minus s. This is your minus 1. And this is your minus 2. That is equals to 0. So this will give you that this s square plus 2s plus 1 y of s equals to s plus 3. So this y of s now we can write as s plus 3 upon this one is square plus 2s plus 1 is s plus 1 square. So again same y of s we have got in the first problem, question number 6. So again we can write this 2 plus s plus 1 upon s plus 1 that square. So we'll have 2 upon s plus 1 square plus 1 upon s plus 1. So now we can take inverse Laplace. So taking inverse Laplace, so y of t. So we know that 1 upon s squared is ramp signal tut. but it is s is replaced by s plus 1, e to the power minus t is multiplied. So it is 2, it's t, e to the power minus t and ut. Check. So 1 upon a square, Laplace is t ut. And if it is 1 upon s plus a, that whole square, that is e to the power minus a t, t into ut. Okay, so that we have done. And only 2 is coefficient is given there. So 1 upon s plus 1 whole square, it's a t ut multiplied by e to the power minus t. Right, and plus 1 upon s plus 1 is simply e to the power minus t ut. Okay, so what will get? 2t e to the power minus t plus e to the power minus t ut. Okay, so that okay, they have simply, but it is simply the answer is V, because this is this one. So we can take common 1 minus 2t plus 2t e to the power minus 2t ut. Okay, so 1 plus this one is correct answer, B. Right? So whenever you will get this type of differential equation, first take Laplace transform, use the initial conditions properly, then get the capital Y of S, then take inverse Laplace. You will get time domain signal. That is your solution. Okay, and I hope you have enjoyed this lecture, and please subscribe my channel. I'll be uploading many videos regarding different subjects like signal systems, circuit theory, EM theory, control system, many more. Okay, so keep on watching my channel. Thank you.